Okay, good morning, everybody, and thank you for staying along for the duration of the course. So that has been quite a few lectures on the quantification of the electron microscopy and on the use of the deep convolutional networks for the image analysis in EM. So today we are starting the third part of the course, where we are going to talk about the decision making and generally incorporation of the automatization experiment in the electron microscopy workflow. So we are going to focus on the Gaussian processes and the Bayesian optimization, simply because that these methods are, in some sense, the mainstay of the current automated experiment. In the end of the course, we will also have an introductory lecture of the reinforcement learning. But for the time being, there are reasons why Bayesian optimization is the way to go. So let's start with the description of the typical day in the lab for the electron microscopy. So imagine that you have a project where you have some material that you want to study. So obviously the work starts well before you get to the electron microscopy lab. You need to get a sample, you need to prepare the sample, you need to put sample in the load lock. But let's assume that all of this preparatory work is done and you have a sample inside the microscope. So what do you do next? So obviously the first thing that you do is you tune the microscope to get the optimal resolution. After that, you start with getting the overview scan of your sample to visualize the features of interest. And then the typical process of the microscopy operation starts with selecting some region to zoom in on the sample. So let's assume that I want to study the nanoparticles having interesting plasmonic properties. So I will zoom in on the sample. Let's assume that for whatever reason I don't like this region, I will zoom out. I will choose another region. I will zoom in here. I can repeat this process several times, sort of zoom in and zoom out several times. Finally, I identify the region of the material that is interesting. And once I found the region that is interesting, then I'm going to do the EELS measurements, either the individual EELS curves or the hyperspectral imaging. I acquire the whole data set. And then typically it's the end of the day, I go home, and the next day I'm going to analyze this data set. So the question that you may ask is, what does it take to make this process automated? So if we want to have automated microscopes, what do we have to do? Obviously, it requires two components. Component number one is the capability to issue the commands to the microscope to perform certain operations. So the machine learning agent should be able to, so probably it's not going to be able to load samples, at least initially. But ideally, the machine learning agent should be able to initiate the tuning of the microscope. So machine learning agent should be able to issue the command to perform the overview scan and tune the parameters. So it should be able to issue the command to zoom in and position the probe at the selected locations and initiate the spectrum acquisition. In fact, virtually all operations that we perform on the electron microscope or any other probe microscope for that matter can be expressed in the minimum control language. So this is something that the human operators can do. By the same logic, if we want the machine learning agent to operate the microscope, the machine learning agent should have access to those commands as well. So where are we with this type of access? And the answer is that things are developing very, very fast now, because a few years ago, it was only companies like Neon that offered the Swift that allows you to issue the commands to the instrument. So next week is going to be the microscopy microanalysis meeting, where the many companies, including Joule, Thermo Fisher, so the companies with the really large markets and large number of the tools in the field, start to offer the APIs that allow to deploy Python codes as a part of the microscope operation. So the difference compared to even a year ago is drastic. However, there is a second part to this process, which is the decision making. And the decision making is traditionally done by the human operator. So human selects the initial region for the overview scan. Human selects the locations to zoom in and zoom out. Human select the regions to perform the spectroscopic studies. And this creates a very interesting situation because in order to make the automated microscope, we actually need to first and foremost understand how human makes decisions during the microscopy experiment. And this kind of difficult because this is not something that you typically read in the textbook. This is something that you learn by virtue of being a microscopist, by virtue of training, and by virtue of being an active scientist. So what are the type of questions that we can ask? So the first one is what can we say about the structure, right? So if we have a new material, a new system, first we are driven by curiosity to understand what is going on here. After that, we have some amount of logic in or some prior knowledge of physics. For example, let's assume that in the case of these plasmonic nanoparticles, we know that the interesting functionalities are expected at certain structural elements. So by virtue of reading the textbook or papers by our theory collaborators or working with the theorists, we expect that the interesting functionalities can manifest either on corners or they manifest in the regions when you have the double layer of these nanoparticles, or they manifest at the layers where regions where the different type of ordering exists. So in this case, the particles are ordered in one orientation, and here the orientation is rotated by 45 degrees. So this is one way to look at it. We can look at the image and make the decision based on structure, and we can select the regions where to perform measurements based on structure. So if you make a connection to the previous several lectures about the deep convolutional networks, that would be absolutely correct connection, because if we know in advance what is the aspect of the structure that we're interested in, we can tell the deep convolutional network to identify these features and perform the specific measurements of those features only. And this is your pathway to the low beam damage imaging, acquisition of the large number of the spectral data sets, and so on and so forth. However, there is another way to find the interesting regions. Imagine that rather than being interested in specific structural elements, we are interested in specific spectral elements. For example, if I take the spectrum from 3 locations of this image, in 2 locations, I will have only a single peak in the IL spectrum. And in one location, which is shown by the orange curve, I can see the shoulder on this peak. And the question I can ask is, how can I find the regions with where the shoulder manifests without running ILS measurements everywhere? So this is the example of the automated experiment that goes beyond human level. So human cannot do that. So we can only study the grid, perform the grid measurements, and then analyze the results. So obviously, these are the experimental measurements that are possible in the context of running the microscope without knowing much outside of that. So this being said, there are several keywords that I would like to kind of share with you, because they are absolutely required to translate from the language of the domain, meaning microscopy, to the language of the machine learning. So the first keyword is the objective of the experiment. So objective is typically defined in the outside context. So the objective of the experiment is, for example, understand the physics of the plasmonic responses in these nanoparticle systems. Or the objective of my program can be to develop the new phosphors for the computer screens. Or it can be the development of the electrochromic materials for the windows. So objective is something, big picture that we have in mind. And this is not something that we can accomplish during the experiment. So in fact, the connection between our experimental result and the purpose of the development of the electrochromic windows can be fairly diffuse. However, what we do introduce as the topic of the experiment is the reward. So reward is something that we can quantitatively measure. So this is in some sense a number of whether the experiment has been successful or not. For example, the reward can be, I want to measure the plasmonic properties of 1,000 particles. It's not a particularly useful thing, but that's an example of the quantitative result. Or the reward can be I want to learn the structure property relationship, meaning the relationship between the local structure and the plasmonic spectrum. So my reward in this case would be how well can I predict the plasmonic spectrum given the observation of the local structure. And obviously the way I quantify the reward is the mean square error of such prediction. The reward can be more subtle. For example, I can say that I want to understand the physics of the plasmonic interaction, meaning build the constitutive model, for example, the dielectric function of this plasmonic nanoparticles, which allow me to predict whatever is going to happen for any possible arrangement of these particles. So the important thing about the reward is that, unlike the objective, we actually know it in the end of the experiment. And the myopic reward is the type of reward that is available at each experimental step. For example, I can improve my prediction of the structure property relationship between the structures and the plasmonic spectra based on each experimental step. So there are two more words that we need to know. So one word is the value. So value is essentially an anticipated reward. So the way we do it, the thing is that we don't necessarily know the reward at each step. Sometimes the reward is available only in the end of the experiment. So if the reward is available only in the end of the experiment, then we need to somehow plan our experimental activity. For example, I want to do measurements here, then here, then here. And the way I do that is by ascribing a value for each individual step. Final concept that we want to introduce is policy. So policy basically means what is that we are going to do dependent on observation. So if I observe this type of particle structure, what do? Do I perform the yields measurement, or do I go to the different location? So for those of you who are familiar with the machine learning, this language would be very reminiscent of the reinforcement learning, and that's exactly where it comes from. There is a big difference, however, that when you study the classical reinforcement learning, the rewards are sort of given to you. So the reinforcement learning community focuses on developing algorithms that operate in the environments where the rewards are already defined. For example, you want to play Mario game, or you want to drive the Mario Kart, or operate the industrial robot. When you try to apply these concepts in the experimental setting, the most difficult part is actually to define the rewards in such a way that you can communicate them to the machine learning algorithm. This is absolutely not trivial. And in fact, if we learn how to do that, then our life in building autonomous microscopes will become considerably easier, because we would be simply able to take the page from the standard reinforcement learning textbook. But this step connection between the objectives and rewards, this is really difficult. So why do we need automated experiments? So the example of the yield spectrum can be one example. Another, if we go a little bit to the outside context, another example is something like sample selection. For example, if we want to study the results of multiple experiments, so you have a colleague who synthesizes ceramics, or makes the metallic parts, or makes combinatorial spread libraries, we always have a question of the sample selection. So if somebody if you have multiple samples, how do you choose the right one to actually perform the measurement? The measurements are expensive. So typical example for this is the combinatorial library. So they're relatively easy to make. People have been doing it for 30 years. So this is the example of combinatorial library of bismuth ferrite, which is pure bismuth ferrite on one end, doped bismuth ferrite on the other end. So this is essentially this line on the phase diagram. The problem with this, so this library encodes the full, the full phase diagram. And we can use electron microscopy to study it. So for the ferroelectric phase, we can visualize the beautiful ferroelectric domains. So there is a reason why we started the course with the quantitative electron microscopy, because that's what requires to take the image like this and extract polarization orientations. On the other end of the phase diagram, we have the orthorhombic material, so there is no polarization whatsoever. And somewhere in the middle, we see this very interesting splotchy phases. So the question is, what can we learn from it? And more importantly, let's assume I have done 3 measurements. How do I choose location for 4th and 5th measurements? I need to be considerate about it because, again, each measurement is the time on the FIB and it's time on the microscope and it's time analyzing data. And obviously, my selection of the new locations for measurements have to be given by some anticipation. I cannot just do it based on curiosity. So, what is the difficulty here? So the difficulty here is that any experiment, even relatively simple experiments such as running the electron microscope, basically opens the combinatorial space of opportunities. So imagine that I'm sitting in front of the microscope and I make a first decision. So based on the results on the first decision, I will get the new information. And based on this new information, I'm going to make the second decision. And then I'm going to make the third decision. The rate at which we are making these decisions, I mean, it's human limited. So maybe I have to make a decision every few minutes. But if I spend 10 hours in front of the microscope, that's a lot of decisions to make. And the number of total possibilities in this case is going to be growing exponentially. So that's actually the reason why in most cases, we actually cannot invest in just accelerating the experiment, because if the number of the possible decisions grows exponentially, investing into doing things fast can help us a little bit, but really not that much. So the amount of the new information that we learn is going to grow as the logarithm of your throughput, not even as a linear function. Also, an important thing is that when we make decisions, we typically make them not based on the data only. So in any experimental, any scientific experiment, we constantly kind of have this feedback between the theory and experiment. So theory basically tells us that this is what we're interested in, this is the hypothesis we make. Generally, the experiment planning or the decisions that we make try to come up with the best way to address this hypothesis. So then we run the experiment, meaning making the measurement. And based on the result of the experiment, we either falsify the hypothesis, so we figure out whether it is right or wrong, or we make a serendipitous discovery. So we see something that we didn't expect. And then we use this new knowledge to essentially update our theory. So this cycle between the theory and experiment is absolutely constant everywhere, and it is deeply hierarchical. So I make some implicit hypothesis when I choose the next location for the measurement, for the yields measurement. And I do it within the essentially 5 minutes that I'm running the microscope. But I'm also making this big cycle when I perform the measurements in one day, and then I go on and select the next sample for the measurement. So again, this is something that is not very common for machine learning. And one of the things that you might have noticed in the last half a year was this exponential growth of the interest toward the large language models. And in fact, some of my collaborators in the at the Carnegie Mellon started to actually incorporate the large language models as the part of the experiment in the chemical lab. The problem with the large language model or any large pre-trained machine learning model that it has access only to the past knowledge. So it integrates the past knowledge, but it can give you only the part of the answer. If you have a fundamentally new sample under the microscope, large language model is not going to help you choose the next location. You can use it as an advisor that allows you to ask questions like, if I want to understand the origins of dislocation activity in this material, what should I explore? But it is not going to be able to run the microscope directly, at least not in the pure form. In fact, folks who work on the automated labs in the chemistry or biology understand this very well. And typically, the large language model becomes a part of a much more complex setup that combines search, code execution, exploration of the enterprise-specific documents, and the lab automation. So in other words, it can help us, but it's not going to do the low-level decisions. And the third thing that I wanted to bring is something that we need to be prepared for when we think about the automated experiment. So classically, so until now, the way that we run the microscopes is that the human issues the command to the microscope. Microscope provides the basic outputs in the form of images and spectra, and humans make decisions based on these raw microscope outputs. We can expect that addition of the machine learning agent in the loop is going to change that. Because imagine the situation when we have the machine learning agent that issues the primitive commands and has access to the raw imaging and spectral data. So what is going to be the role of the human in this process? And the answer is, of course, human can do two things. So one thing is to overview the machine learning agent. Another thing is that human can intervene. So it's, think about it like having a car with the autopilot. So actually cars kind of don't have them for the time being, but imagine that you have the automated car. So human wants to have some degree of control and observe how the AI runs it. But let's assume that this is a basic level of intervention. So let's assume that our role is to oversee the machine learning agent. So there are two things we need in this case. One is we need to somehow monitor the activity of the machine learning agent. So what it is doing, what is that we are learning? Or in the language that I introduced 2 minutes ago, what is how fast we are accomplishing our reward? And the second thing is that we actually need to modify the behavior of the ML agent. So for the time being, all the examples of the automated experiments I have seen suggest that they're not going to be truly autonomous. In fact, we have a human who oversees the ML agent, and humans can modify the behavior of the ML agent. And the way you do it is through changing its priorities, so affecting the rewards, or changing its policies, how it behaves in the certain situations. So interestingly enough, if you think that transition from normal microscope to the autonomous microscope would be like a transition from, let's say, Toyota to Lamborghini, it's absolutely not the case. So it's not even a transition from bike to Lamborghini. It would be more like a transition from the horse to driving a car, because our controls are going totally different. So if we drive a bike, we actually have the wheels that kind of move the car. We have the steering wheel that allows us to drive where we want. We rely on the human intelligence to choose the direction. So if we drive the Lamborghini, it's the same thing. So we have obviously an engine that helps us drive, but the principles are exactly the same. So for ML agent, situation is different. So we are really going to completely new environment. So this being said, let's kind of go back to a little bit to the original lecture and see how this process can be started. So as I mentioned a year ago, the situation would be that you need to somehow get the controls to your microscope. By now, it looks like industry is going to give us the API that allow to deploy the code on the real world tools. So the question becomes, what is that we need to do to implement the automated microscopy? So again, we need to understand the problem. So understanding of the problem is something that a domain scientist should do. And for each of you, it would be your own problem that you want to solve. You just need to translate it into the machine learning language. So you need to know a little bit of machine learning. So that's exactly what we are hoping to accomplish in this course. So some basic concept. Need to develop the code. So for the test examples, the notebooks that we provide should be sufficient. Operationalization is a little bit different. You kind of need to dig deeper and work with the Microsoft specific software, but then you need to implement it and kind of get to work on it. So if it sounds that there are a lot of new words that are not quite clear and difficult to comprehend, like policy, reward, acquisition function, myopic policy, well, it is the same thing for machine learning community. For them, experimental science is also very complicated. It's a small data, causal laws, physics laws, active learning, and so on. So let's kind of following the same logic is how are we going to do that? So as I said before, we need to define your problem. We need to define our hyperlanguage. So that's already done for us. Then we need to define the workflow in terms of hyperlanguage. So for those of you that are microscopists, that's actually understandable. And then it's time to dig into the code and understand how it works. And here we are going to start with the very basic of the active learning, which is the Gaussian processes. So Gaussian processing is a very interesting area of the machine learning, or in fact, Gaussian processes existed long before machine learning in the context of the statistics. But it is very germane to the whole idea of how do we make decisions. And let's start with a very, very simple example. Imagine that we have some parameter space, so in this case, one-dimensional, and we have done two measurements. This can be anything whatsoever. It can be the contrast on the screen between two locations. It can be the resolution for the two values of the aberration character setting. It can be anything you can think about whatsoever. It can be even an example from material science. It can be lattice parameter on the band gap as a function of composition. So machine learning is very agnostic to the specific domains. And in some sense, it's its difficulty because once you start to learn machine learning, you instantly encounter the new concept that don't seem to have a intrinsic connection to the everyday physical reality. So nonetheless, let's assume that we've done this measurement. And then the question becomes, how do we extrapolate? So what do we think is happening between these 2 points? And of course, for all of us, either coming from physics domain or from the data science domain, the obvious thing to do is to connect these points by the straight line. So basically what we are saying is that for this, and this parameter values, we expect the value of this function to lay on this straight line directly. And that's perfect outcome. If you read the book about the data methods, they will do the linear interpolation. If you read a physics textbook, probably starting from somewhere in the mid-school, you will also draw a straight line. Now, the interesting part becomes how are we going to choose where to do the next measurement. So the obvious thing to do is to take the next measurement halfway between these points. So somehow we make a decision that the most informative location is going to be in between. So we are not going to take like measurement here. We are not going to take measurement here. We are going to take it at the maximum separation from the points. So the reason why I'm saying it is because if you want to run an automated experiment in electron microscopy, you will have to make exactly the same decisions. You make a ILS measurements on 2 locations of the image. How are you going to choose the third location? Except that if you want to do it by yourself, you can do that. But if you need, if you want machine learning agent to do that, you need to somehow communicate this decision to understand how machine learning agent is going to make decisions. So decisions have consequences. So let's assume that we perform the measurement on this location, and now we have this value. So what are we going to do next? So one option is to say that this dependence is really not a straight line. It is more like a parabola. It's a very reasonable argument. We can always draw a parabola through 3 points. But this is already the case where things become non-trivial. Because imagine that for whatever reason, you are absolutely certain that the dependence between this function and this argument should be linear. And in this case, you can say that it is a linear dependence. However, your measurements are coming with the noise. So notice a very, very important thing, that in this particular case, if we trust our data absolutely, we are going to connect these points by parabola. If we have reasons to believe, so we have a prior knowledge that the dependence between the function and argument is linear, but at the same time, we don't trust our measurements absolutely. We say that the measurements come with the noise. We draw a straight line. So everything that we are doing in the scientific decision-making is going to be a balance between the data, which gives us something new, experimental results, and the prior beliefs that we use to incorporate them. And we can choose to believe the data absolutely, so that's one limit. Or we can choose to believe the previous laws absolutely. That's another limit. Practically, of course, both are not the right way to proceed. We somehow need to match the beliefs between the prior knowledge and the data that we are acquiring. And in fact, we actually use the mismatch between this to actually plan our subsequent experiment. So this is a physicist viewpoint. So let's look at the same problem from slightly different angle and ask ourselves a question: what do we know if we don't know anything? So in this case, I have stayed with the measurements. I have stayed with the belief that my function can be either linear or it can be parabolic. And of course, if I get more data, I will make it more complicated. But what if we take a very different approach and say that, look, I don't know anything about the system. How can I define the unknown function in this case? And of course, in the case when you really don't know anything, you're going to say that your function can be just a random number. So to be honest, there is still some assumptions here. For example, random numbers come from the certain distribution, but at least in this case, the location at one point is absolutely unrelated to location to a different point. So if you do measurement on this location, and this location, you are not going to learn anything about the measurements here, here, and here. So there is no predictive power whatsoever. So as we've seen in the example before, in physics, we typically assume certain functional form. How would the data scientist do that? And it turns out that this is exactly what the Gaussian processes is. So in the most simple case, the Gaussian process is basically saying that we postulate that there is some correlation between the measurements between the adjacent locations. So in other words, whatever the value of the function is at one location, it would be correlated with the value of the function in the adjacent location. So this correlation is given by the so-called kernel. So kernel is essentially equivalent of the correlation function, except that it is parameterized by a certain form. And it becomes a very interesting object where we don't know anything about the value of the function. So for each value of x, y can be anything. However, we actually learn something about how the value at one location is correlated to the value in another location. It is a very unusual concept. It kind of takes quite some time to kind of come to grips with that, but it's very easy to illustrate. So for example, let's look at how does this change the way these functions behave. So this is the samples from the Gaussian prior when our correlation length is 100th. So if we say that our correlation length is 1/10, you can see that these curves become considerably more smooth. And if our values is 1, then become even more smoother. So basically, this is a collection of the curves that somehow correlated to each other. So now let's switch from the lecture to the notebook. So the notebooks, as before, in the folder on the is on the folder on the GitHub, and go to the notebook which is called 0 GPAX GPA, and let me share the screen with you. Where is it? Here we go. And then we are going to play with these objects. So in the beginning, so in this case for Gaussian processing, we are using the GPAX library developed by Maxim Ziadinov. So obviously now there are multiple solutions for the Bayesian optimization, kind of most notably BotTorch, developed by the Facebook. There are GP flow, there are simple Gaussian processes as a part of the scikit-learn. So why GPAX was developed? I mean, first of all, it was developed before BotOrg, or before BotOrg became public. Secondly, the important part about the GPAX is that it is designed specifically for the use in experiment. So it's designed for using with the relatively small data, run fast, and provide the most useful functions in the easy to use form. So in other words, we want to make it simple as opposed to write the long BotOrg or Pyro programs. So let's start with installing the GPAX. So it should be fairly fast. And then one more important thing to mention is that GPAX actually has been used for the automated experiment. So if you've seen the papers on the automated electron and scanning probe microscopy from our group, this was the case of the GPAX connected to the real world microscopes producing result. So in this case, it works. So anyway, we installed the GPAX. We installed the relative necessary libraries. So all we need is the NumPy and matplotlib and NumPy in order to kind of create the backend for the GPAX. And let's start with a very simple example of the function that we want to optimize in some way. So in this case, the function is the ground truth. So this is something, this is how the nature behaves, and this is what we want to discover in the automated experiment. And but we don't know that. So the purpose of the experiment is either to learn the function or find the minimum of the function. So practically think about it that this can be the dependence of the resolution or the quality of the image on the setting of the aberration character, for example, or it can be anything else whatsoever. So the thing is that we don't know the function by itself, but we can measure it in some locations. So one very important thing here is that we have a ground truth function. So we choose something interesting because it will help us to illustrate the how the GP works, but we don't have access to the function itself. We measure it, and we measure it with the addition of some noise. This is exceptionally important element, and I'm going to return to it quite a few times when I talk about the priors of the noise and the noise itself. You will see that it actually plays a really big role. So the second thing we are going to do is we are going to generate several noisy observations of the function. So this is example of the ground truth, the blue curve, and the measurements, the crosses here. So let's assume that in this case, we perform the measurement with the, so this is our number of points. This is our ground truth. Our X is, this is where we take the measurements. This is where we do the where we perform the measurement points. So we can say that the noise is going to be higher. For example, if I define the noise equal to 1, you will see that there is a considerable difference between the position of the ground truth and the measurement. So if I define the noise to be 0.1, you can see that the measurements are now much closer to the ground truth. So the key thing here is that we postulate that there is a ground truth. We postulate that the measurements are a representation of the ground truth plus some noise. And we argue that noise has some distribution. So in our case, we use the Gaussian distribution. It can be pretty much anything else as long as the mean function is 0. So now we do the next thing. And our next step is to define the Gaussian process. So the important thing here is that when we define a Gaussian process, we need to start with some priors. So priors is essentially our belief in what the noise in the system is. This is the noise prior, and our belief in the strength of correlations in the system. So why does belief matter? The belief matter because we don't really know what is our data generation process. We postulate that it is random noise, but we don't know the exact distribution. Therefore, we need to provide the initial belief of what we think the noise is. And I will show you the example that it actually pretty dangerous to be both too optimistic and too pessimistic. So we'll go through that, but let's start with just going through the basic mechanism of the Gaussian process once. So first thing we do is we define the noise prior. So in this case, you can see that this is a half normal distribution. So noise magnitude can be only positive. And we say that it is something like 0.1. So notice that in this case, our noise and our belief in what noise is are the same. So then we define the priors on the Gaussian process kernel. So for the simple kernel like RBF, we have only two parameters. One is length scale, another is scale. So length scale is correlation in X domain. Scale is basically the vertical correlation. So notice that in this case, we, for illustrative purposes, we choose that the distribution of the kernel length scale is uniform, meaning that kernel can be anywhere between 0.1 and 5, but it cannot be bigger than 5 and can be small. It cannot be smaller than 0.1. Again, I will show why it matters. We can visualize these distributions just to kind of have an idea of how they look like for convenience, and then we can run the Gaussian process. So define the single step. So notice that the process is actually very simple. So we start with the definition of the random keys, so they're necessary for the algorithm. We define the model. So the model in this case is one-dimensional. We use the Mattern kernel. So it really kind of doesn't matter which one we use. We can change it to the RBF. Then we fit the model, and then we predict the value of the function. So that's it, very, very simple. And our objective function is the total uncertainty. So let's go through this process, and now let's run the whole Gaussian process of the discovery of the new function. So what are we going to do here? So let's go through this code step by step, because that's how we run the automated experiments, actually. So we define the number of the experimental steps, kind of goes without saying. Then we make the step of our measurement. Then the key things happen. We identify the point where there is a maximum uncertainty. So what do I mean by that? So when we run the Gaussian process, we start, so you will get used to this demonstration. So we always start with the initial measurements. So this crosses is what the algorithm has access for. And we also, for convenience of illustration, show the ground truth measurement. However, ground truth serves only to illustrate the process. Practically, we don't know that. So it's a very important thing. So you kind of need to develop a little bit of the split vision. So when you run the active learning experiment for training using the model data or the known ground truth, so when you just kind of learn things, you have access both to the experimental data, meaning this crosses, and the access to the ground truth. When you run the active experiment, you don't have access to the ground truth. So the reason why we are going through the large number of the model examples is actually because we want to understand the general principles, and we expect that in the real world, the algorithm will behave the same way as in the model environment. The only difference is that in the real world, we of course don't know the ground truth. So let's see what the algorithm is doing. So imagine that we start with these measurements. So we tell the algorithm that given the measurements in these 4 locations, can you please try to reconstruct the function and the uncertainty of this function? And what the algorithm does, it basically does the most kind of natural way. It sort of draws this blue line which is the algorithm estimate of how the function should look like. And it also gives us this red area, which is illustrates the uncertainty. So this capability to define reconstruct the function and reconstruct its uncertainty, that's actually what makes the Gaussian processing an extremely unique method for making the automated experiment. Because with this information in hand, you can choose the next location for the measurement. And the obvious way to do that is to choose the next measurement location in such a way that next measurement is done in the point with the maximum uncertainty. So we are uncertain what the value of the function in these locations is, but in this location, our uncertainty is maximum. Therefore, we expect that if we do the measurement here, our relative information gain would be fastest. So let's do that. So this uncertainty in this case is represented by the acquisition function. So we'll talk at more detail about what it is and why it is called acquisition function in the first place. And acquisition function is essentially the equivalent of the human decision making. You always make a decision at the maximum of the acquisition function. So in this case, the maximum corresponds to this location. So we perform the measurement here. And then given the new measurement, we run the experiment, we recalculate the Gaussian process one more time. So now we have done measurement in these 5 locations. Again, we reconstruct our curve, we reconstruct the uncertainty, we take the measurement at the point with the largest uncertainty. So now this location is here. So now the largest uncertainty is here. So we repeat the process over and over again. So if we do it sufficient number of times, then our blue curves start to look more and more like our ground truth measurements. But notice one very important thing, that despite all these measurements, we were never able to capture this zigzags over here. At the same time, if you read any books or papers about the Gaussian processes, you will find the often made a statement that Gaussian processes always converge to the ground truth function. It's actually true, except that depending on how you configure it, determines how fast it can actually converge to that. So if you set it correctly, it can converge in a very small number of steps. If you kind of choose your parameters poorly, it may take effectively forever. Given that we always deal with the experimental problems, we really need to learn how to tune them properly. So anyway, if we continue this experiment for 10 steps, you can see that our Gaussian process gets closer and closer to the curve, but ultimately it was not able to discover this minimum. So let's just do a little bit of tweak here. So and try to understand why did it happen. So let's start with the case where our measurements are actually more precise. So let's assume that our noise in our measurements is 0.1. So our measurements are representing the curve much better. So let's assume that our measurements are more precise now. So our belief in the noise is that the noise is smaller. So the measurements are precise. And let's run this Gaussian process one more time. So let's see what happens in this case. So notice that in this case, it runs very fast because we have a relatively small number of points. Also notice that it's a good practice to choose the seed for the measurements sufficiently precisely. So notice, and the process started. So then our measurements can be reproduced. So the process started. Notice a very interesting difference now. So now at the points where the measurements are actually done, this red area is considerably smaller. So why is it happening? It happens because when our Gaussian process works, it simultaneously updates the length scale, and the noise. So these are the kernel parameters that are learned during the active experiment. So ultimately, for the point where the measurements are taken, the uncertainty would be dependent on the noise posterior. So this is what the algorithm believes the noise is. And if algorithm is certain that the noise is small or noise is zero, then in these locations, we will see no red interval. So the algorithm is certain. If the noise is high, then it would be high uncertainty. So see what happens in this case. So the algorithm continues to explore our parameter space. It still finds the locations in these points. And for the time being, it repeated the process that we've seen before. So these are the measurement points. This is our reconstructed curve, so the posterior mean. And this is our ground truth curve. And you can see that at this stage of the experiment, we have not discovered any of this wiggly behavior. And to be absolutely honest, we don't expect algorithm to do that, right? So if I give you these points only, so forget about the teal curve for the time being, this would be your best guess about the interpolation as well. But this is where the magic happens. So currently, the algorithm is also calculates the uncertainties, and the maximum uncertainty now is in this location. So you see the maximum of the acquisition function corresponds to this minimum. So our next experimental step is actually in this location. So see what happens. Once we perform the measurement on this location, we get the experimental point, which is completely different from the initial expectation. And this is the key part, which is common for science that we do as humans and science which is done by the automated algorithms, is that how much do you trust the result of the experiment if it doesn't fit nicely with your model? If we do the measurement here and we measured the point close to this location, then algorithm is done. It will say that, hey, I can predict over your whole parameter space. The uncertainties is very small. I think we are good. But the algorithm makes the measurement here and comes up with a number which is completely off. So whether to believe in this number or not depends on our noise priors. Our noise priors were chosen to be sufficiently small. Algorithm is absolutely convinced that this point is real. And if this point is real, that means that we need to rethink what is the behavior of the function. So all of a sudden, we have identified the new regions where we have high uncertainty. So we no longer believe the values here, here, and here. We say that these measurement points now have high uncertainty, which basically means that we sort of repeat the cycle. Now we perform the measurement on this location, and lo and behold, we found this minimum. Now the highest uncertainties are here and here. So we repeat the measurement in this location. So when we repeat the measurement in this location, we found this minimum. So as you can expect, the next measurement would be here, and then the measurement after that would be here. And that's exactly what happens. So now in the 10 steps, we have discovered our function sufficiently close, or kind of sufficiently close for the algorithm. So that's exactly the idea of the Gaussian processing. And this is exactly the reason why it is so vital to keep track of the process and keep track of the priors. So let me illustrate the posterior distributions. So this is essentially all the curves that are consistent with the observation. So this is a very convenient mechanism to understand what is happening under the hood of the Gaussian process. So it may take a little bit time to observe it. So in this case, it's not interesting because all of them are essentially close to the ground truth. Now, let's play a little bit more with the algorithm and again highlight this role of the prior belief. So let's assume that my real noise is small. So I assume that my measurements are precise. And let's assume that my noise prior is actually large and is equal to 1. So, by the way, in this notebook, you need to kind of restart the process from the beginning, because otherwise we don't delete the values obtained in the model. So let's assume that my noise is very, very high. My noise prior very high. High noise prior means that I don't trust my measurements whatsoever. I think they're very unreliable. Let's see how the algorithm behaves in this case. So we continue our evaluation. Let's see what happens. So notice that we choose the noise prior to be 10. Now the noise prior is about 8. So basically what happens that if these are my measurements, this is what algorithm reconstructs. So it's absolutely no relationship with the gross truth. And that's kind of what we expected, because we said that we don't trust our measurements at all. So if we continue the process, you will see that it will somehow start to converge. And the important part of this convergence is that the values of the noise are becoming smaller and smaller. So in the beginning, you will see that the algorithm doesn't try to learn the function very well, and it's kind of updates to the length scale and scale are more or less random. But basically what it learns is that I actually can trust my measurements more than I thought I can. So the values of the noise start to decrease. So it goes from 8 to 5 to 2.6 to 0.69. So you see that after several iterations, we actually learn to trust our measurements more. So that's obviously not the most effective way to run the active experiment, but that's how it works. Another thing you will notice is that, so remember that in science, we always talk about the reproducibility. So one way we can deal with the understand the noise issue is by running the measurements at the same point of the parameter space. So for example, if we if we think that our noise is high, we can do the measurement several times, and we can use the standard frequency-based statistics in order to estimate the noise level, sort of using the usual dispersion formula, whatever. It's a way to proceed, but that's not the most effective way. So in some sense, when the Gaussian processing-led experiment works, you kind of get this type of information, but you don't have to do the measurement in one location and of the parameter space and take the dispersion. Gaussian process does it in the form of the noise prior. And sometimes it will actually ask you to do the measurements and the specific location. So for example, here it did measurement twice at the end of the interval. But generally, reproducing the measurements is not the most effective strategy to ascertain the reproducibility. So noise prior is generally more effective way of doing that. And then you can see that sometimes your uncertainty can go down, sometimes it can go up. So for example, at this stage of the process, the algorithm thinks that the noise level is low and the measurements are, and the process converged. But now again, you do the measurement at the new location, and lo and behold, you see that the algorithm lost confidence because the new point is actually very different from the prediction. But notice what happened in this case. We, in the beginning, were not confident in our noise. We said that our measurements can be off. At this stage of the experiment, algorithm decided that the noise is low until it did the measurement, which is away from where it should be. And then the algorithm goes back to saying, hey, maybe my noise is actually large after all. So you see that uncertainty associated with the noise increased. However, if we spend some time running the algorithm, so we didn't do it all the way because it will take quite some time, but you see that it starts to converge to the final value, ground truth value. Now let's do one more experiment. So now let's assume that our noise is still small. Let's assume that we can trust our measurements, and we say that our measurements are precise. And let's play a little bit with the length scale of the kernel. So let's assume that somehow I tell my experiment, I'm certain that my correlations should be fairly long range in the system. So what will happen in this case? So I initiate my kernel values. I will run my Gaussian process experiment, and let's see what happens in this case. And if you think about it, you probably already would be able to predict what is going to happen. That if I said that the correlations are very long range, I don't expect to be able to find the final details, to finer details on this ground truth curve. In fact, that's exactly what is going to happen. So if I run the experiment several times, I will see that I will try to the algorithm will find the average shape of the curve. So it's kind of tries to imitate it, but it is not going to be able to reconstruct the fine features, and it will not be able to reconstruct them simply because we did not allow the experiment to do that. We introduced the constraint on the kernel length, so we've used the we use this rigid uniform distribution, and we basically said that the kernel length cannot be smaller than a certain value, which basically means that no matter what the experimental results are, we will not be able to converge to the right answer. And the only way the algorithm would be able to accommodate the fact that the measurement results, so the crosses, are different from the predicted curve is by increasing the noise. So what is going to happen is that the algorithm will proceed, and we will see that the noise becomes larger and larger. So that's not super interesting because, so let's try to do the opposite thing. So now let's assume that we tell our algorithm that our kernel length scale has to be fairly small. So it can be, for example, from 0.1 to 0.5. So let's see what happens in this case. And another interesting thing in this case would be, okay, let's run it twice, one time for the measurements with the low noise. And okay, let me start it again. So one time with the measurements for the low noise and one time for the measurements with the high noise. So let's see what happens in this case. So if you have any questions, feel free to drop them in chat because, as I mentioned, this is a fairly foundational concept for the Gaussian, for the automated experiment. So if you have questions, it's better to go through them in detail. Okay, so what happens in this case? So we have chosen the scenario where the kernel length scales are fairly small. And if it is the case, then the algorithm says the following thing, that I do the measurement here, here, and here. Since my correlation length is small, I can trust these measurements close to this location, but the further I move away, the less belief I have in the measurement result. So this is where the terra incognita for me starts. You will see that the result of the measurement kind of, it looks like that the curve goes down to zero. That's exactly the reason it should behave, because in this case, we deal with the Gaussian process with the zero mean function, meaning that if we're in the terra incognita, the algorithm assumes that the function value is zero. That's actually a very important aspect. And this is something that is very important to understand because this is how you identify the problems with the Gaussian processes. Nonetheless, the progress of the automated experiment would be roughly the same as before. So we do the measurements here and here and here. We are absolutely certain of the results here. So you see no red intervals. We try to reconstruct our curve, so it droops because it tries to be zero away from the point where we are confident, and it gives us the high uncertainty. So again, the automated experiment will choose the location with the largest uncertainty to perform the next measurement. So now the value of the function here is fixed. Then it is going to make the measurement at the point with the next largest uncertainty. Now the value here is fixed. And then if we continue the process several times, you will actually discover the kind of more or less well-behaved behavior. And effectively, eventually, we will converge to the large, right answer. Again, the most important thing becomes how do you understand the dynamics of this uncertainty given by this red curve. So it becomes small only if we are within the kernel lengths from the point where the measurements is taken. So if we run enough number of experiments, our algorithm will converge. Now, let me show you one more example where our kernel length is relatively small and where the noise in the measurement is fairly high. So I will going to take the noise to be, let's say, 0.3. And I'm going to make my belief in noise small. So what it means? It means that in this particular scenario, my measurements are noisy, but I believe that the measurements are precise. So it's a kind of error of being an optimist. So let's see what happens in this case if I run the Gaussian process. So the important thing is that my real measurements are noisy, but my algorithm, I give my algorithm the priors that I believe in noise being real. Actually, in this case, I should have, well, let's see what happens. So what we are going to observe is that ultimately the algorithm will come to conclusion that every noise peak is going to be the real data set, and will try to kind of follow the shape of each noise peak throughout the process. So while it is running, let's look at two more things in this notebook. So I made a list of some experiments that you can try by yourself to understand the basics of the automated experiment. So play with the different balance between the noise and noise prior. So the noise is what the actual measurement noise is. Prior is how much we believe it. So see what happens. So change it to 1. So basically follow this set of experiments, because it will kind of guide you through the process of the Gaussian processing and help development of the algorithm. So speaking about the question, so how do you optimize the parameters when we don't know the ground truth? Is there intuition, or is there some metrics that can quantify how well the algorithm is doing? So this is an excellent question, Sana. So basically, for the answer will depend on the domain. So if I run the experiments on the microscope or any other physical tools, in some sense, I can quantify the parameters from the prior performance of the system or the calibration standards. For example, I know that well-calibrated electron microscope probably gives me the length down to 1%. So if I choose something that is 2 orders of magnitude smaller, that's probably being unreasonable, unless it was Professor Duscher who was calibrating it. If I choose something that 10 times larger, that's being unduly pessimistic. So the good thing is that Gaussian processes are sensitive to selection of the priors, but this sensitivity is fairly mild. So generally, if I quantify the performance of my system and I know the noise, I will choose the noise prior to be twice larger to kind of account for other factors of variability that are not measured in the reproducibility studies, but that's already being sufficiently careful. So in other words, we choose them based on the prior knowledge and quantification of the system. If the behavior of the instrument on some particular day turns out to be completely off because somebody forgot whatever, one of the aberration character elements burned or something like this, then we are out of luck. Then we simply start to pay attention to the instrument behaving totally different. So generally, if you want to build the workflows that allow you to use the Gaussian processing for automated experiment, you start with always running the algorithms on the problem where you know the ground truth, which is kind of close to what you expect to get during the experiment. You tune the parameters for this problem, not precisely within maybe half order of magnitude, and then you expect that these parameters will work well during the experiment. That's the best you can do. The metrics that you get during the Gaussian process, for example, the average uncertainty and parameters like that, they tell you something, but you have seen that I can convince the algorithm to converge to do the measurements in certain locations, make the prediction based on those locations in such a way that it will never find the minima. So that's basically it. We can do better by adding the random measurements. So I will talk about the strategy for adding a little bit of exploration to the process, but generally there is no universal answer. So then one more thing that you will find in this notebook is the exploration of the kernel functions. So there is more radial basis function. The RBF is the simplest example. There are other examples of the kernels, for example, the Mattern or periodic kernels. And you can see the example of how this type of kernels can be incorporated and how they affect the Gaussian process convergence. So I made the example that you can use, but sort of feel free to experiment and see how things behave. So this being said, let me go back to the lecture and show you the second part of the automated experiment, which is going from pure exploration to the exploitation. So let me share the screen. Here we are. Okay, here we go. Open slideshow. So what we learned in the first part of the lecture was the concept of the Gaussian process, the kernel and kernel parameters, kernel prior and noise priors. So we also learned that when we run the automated experiment, prior becomes a posterior. So this is our refined understanding. And then, of course, in the next experiment, posterior is a prior for the new experiment. And in some sense, you might have noticed that I mentioned that the Gaussian process and Bayesian optimizations are called myopic workflows. The reason why they are myopic is because they kind of look ahead for experimental planning only one step ahead. So once I have my experimental results, I plan only the next experiment, then I update my model, and then I plan the next experiment after that. So not all workflows are myopic. So for example, if I want to run the microscope and from time to time I need to make a decision to tune the microscope and then go back to imaging, that's an example of the non-myopic workflow. But we'll talk more about it. So what we're going to look at now is the concept of the Bayesian optimization, and specifically Bayesian optimization based on the Gaussian processes. So as you can conclude from this statement, Bayesian optimization is not necessarily based on the Gaussian processes and can be based on anything. And in general, the way to think about it is that Bayesian optimization is the science, or if you will, art of making decisions one step ahead under uncertainty. So, we are going to look at it in detail in the next 40 minutes. So another word that is absolutely important to know and kind of remember, because this is a foundational element of the process, is the concept of the acquisition function. So acquisition function is a policy or the principle based on which we are making decisions. So let's look at it in a little bit more detail. So you probably recognize this graph. So this is something that we get from our previous collab. So we have our ground truth. So this is our teal curve. We have our experimental measurement points. So these are the locations at which we acquired our parameter space. So we have the measurements here. The blue curve, or the posterior mean, is our best guess about what is the function behavior. So you can see that it goes through the experimental points, but it can be fairly far off from the true ground truth behavior. So imagine that you've done measurements here, 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 and here. You have absolutely no reason to suspect that there should be a minimum over here. And then this red curve is the model answer, is the uncertainty. So the question becomes, how are we going to minimize, so how are we going to run the active experiment? And the answer becomes, depends on what is the purpose of our experiment. So with the classical Gaussian processes, our purpose was to discover the function in the smallest number of steps. So we were a little bit agnostic about the outcome. So we didn't care where the maximum of the function is. We didn't care where the minimum of the function is. All we wanted to do was to discover the function. So this is a pure exploration problem. And in some sense, it's almost like a fundamental scientific research. We just seek to understand the nature as best as we can. But we can imagine a different class of problems where our goal is to find a minimum of this function. And notice that that's a very different problem, because if we want to find the minimum of this function, we need to pay more attention to this region, and this region. But relatively speaking, we should not pay that much attention to this region, because here the values of the function are actually pretty large. So this is actually what the Bayesian optimization is. So this is the picture from the very famous review by Nanda de Freitas in the 2015. And it actually was a very interesting story, because if you wanted to do anything related to the Gaussian processes before the year 2010 or so, you basically have to come from, graduate from one of the maybe 5 groups worldwide that work on the Gaussian processes and Bayesian optimization. And most of the things that you have to do at that time would be to write your own Monte Carlo solver. So maybe 7 years ago, you still had to have a PhD from some of the top computer science programs in the world. So this paper of De Freitas, so it was less than 10 years ago, but it was on the threshold between the Gaussian processing being available to the selected few, even in the computer science world, to the moment when it becomes something that we can actually use as an everyday experimental sciences. So kind of both me and my colleagues are experimentalists, so we learn these methods and develop these methods as applied to the experiment, not from the fundamental viewpoint. But this development has become possible literally over the last 4 or 5 years. Before that, it would be kind of limited to a very narrow part of the community. The difficulty, however, becomes is that many of these concepts are great, but adapting them to the real-world experimental scenarios and developing both the vocabulary and intuition how to do that may be highly non-trivial. So that's the reason why we are running this course in the first place. So anyway, the way the Freitas focuses the Bayesian optimization problem is the following. So imagine that these are our measurements. Based on the measurements, we reconstruct the function. Let's assume we want to find the maximum of this function. So in our case, we wanted to find the minimum. In Nanda's case, he wants to find the maximum. That's kind of almost the same thing. So what are the locations where we are going to explore? And the answer is that it depends on our prediction and uncertainty. So the first type of locations we are going to look at is where our predicted function has high value. So if our predicted function has high value here, we can kind of expect that the maxima can be somewhere here. But there is a second type of locations we want to look at. And this is the locations where the function has high uncertainty. So look at this location and this location. So our predicted function, the red curve, is expected to be small, but our uncertainty is such that we just don't know. There may be maxima here as well. And this is becomes what is called the balance between exploration and exploitation. So the exploitation means that we look for solution close to the maximum, to the expected maximum. Exploration means that we also explore the regions where the uncertainty is sufficiently high. So the next question becomes, how do we balance exploration and exploitation? And the answer depends on what is our experimental budget. So if we can run a lot of experiments, we of course want to favor the exploration first. If our experimental budget is limited, we essentially have only one roll of a dice, then we typically go for the most greedy step. So we are going to look close to the maximum. So how exactly do we balance exploration and exploitation? And this is exactly what the acquisition function is doing. So the acquisition function is the way to combine the prediction of the function and the uncertainty of this prediction. So in the previous lecture, sorry, the first part of the lecture, we saw the example of the Gaussian process driven only by uncertainty. So this is a purely exploratory policy. If we want to balance exploration and exploitation, there are several ways of doing it. So one is the upper confidence bound. So meaning that we predict the value and then we take plus several deltas, meaning the width of the distribution. We have the probability of improvement, which is the integral from current value to the infinity as at the test point. We have expected improvement, and there are always more. So there are infinite number of ways how we can use the predictions in order to formulate our exploratory policy. So there are several blogs that explore them in detail. For example, this is the example of the expected improvement function. And so in this case, you sort of try to predict by how much the measurement and the new point allows you to improve the function value compared to the previous point. Basically, they take some, the best way to learn these policies is by looking at the definition, then trying to apply it in the real world, in the collab as an experiment, and then kind of go forward and backward between the theory and experiment, but developing the hands-on approach. So, and then if we put these elements together, we have the typical Bayesian optimization active experiment. And let's go through it one more time. So we start with the observations and two locations. We reconstruct the function and its uncertainty, typically using the Gaussian process. But any other model that gives us the prediction and uncertainty will work. So we can use ensemble networks, we can use decision trees, we can choose any algorithm that you want. So once we've done it, based on the predicted function and its uncertainty, we are going to calculate the acquisition function. So acquisition function defines the policy by which we choose the next location. And it defines the policy by introducing some balance between the uncertainty and prediction. The acquisition function can favor exploration more. Then we do the next experiment in the locations when the uncertainty is largest. Exploration function acquisition function can be greedy. If it is greedy, then we run the experiment where we expect to get the bigger answer. So greedy policies are dangerous because they can force us to end up being in the local minimum. Fully exploratory policies are better, but they take longer time. So if your experimental budget is large, go for exploration first. If your experimental budget is limited, you have to kind of go for greedy methods. So then we do the measurements. And once we're in the location of the maximum of the acquisition function, and then we repeat the process. We reconstruct our function again. We calculate our uncertainties again. We recalculate the acquisition function. We do the measurement where in the maximum of the acquisition function. So this is the cycle of the Gaussian processes, of the Bayesian optimization. If you are going to apply it for the real world problems in microscopy and imaging, there is a number of ways how it can be extended. So for example, you can also say that if you have a maximum of the acquisition function, but the maximum is fairly shallow, meaning that there are, let's say, 5 maxima which are far from each other, but the values of acquisition function at this maxima are comparable, then a better approach can be to choose the one which is also further away from where you are now in space. So this is a kind of science of the decision-making in the automated experiment. It's virtually unexplored, but I'll show you a few examples of how it can be done in some of the next lectures. So just an example of the Bayesian optimization, I mean, we of course can use it for more problems than microscopy. We can use it for theoretical models, we can use it for tuning the microscope, we can use it for materials discovery. So this is one of the first examples where we used it to find on the theoretical models. So it was the time in the beginning of the COVID when microscopes were not an option. So what you see on this graph is the ground truth behavior. This is the heat capacities in some Ising model. And this is how the greedy Gaussian process actually finds this maxima by exploring the parameter space. So these are the measured points, and this is the reconstruction. So reconstruction, you compare this one to this one, and here you see the greedy acquisition process. So as you can see, the algorithm in the beginning started to do the measurements at one location. So let's see. So in this case, we ran it for several hundred steps. So the algorithm first starts the measurement in this location, then it relatively fast finds this segment, and then it basically greedy extends the exploration of the parameter space until it finds this full structure, and it pays exactly zero attention to the values which are not on this maxima. And as you can imagine, this strategy worked because in this case, we know that the phase transition regions have to be connected to each other. That's a fundamental physics. But if there was some phase transition here and here, we of course will never find it with the greedy algorithm. So anyway, let's go to the next collab and see how the whole process works in the real world scenario. So let me share the notebook with you. So it's also on the GitHub, and the title of the notebook is OneGPX BOAE. So many elements here would be similar to that of the first notebook, but let's go through it in the detail and unpack some of these concepts and see how they work in real world. So in this case, we primarily look at the upper confidence bound acquisition function. So upper confidence bound is just a linear combination of the prediction and uncertainty. So this is our predicted function value. This is our uncertainty. Beta is basically the parameter that allow us to balance the exploration and exploitation. So if we send the beta to be very small, then our algorithm becomes greedy. Then essentially our acquisition function is just the prediction. If we send beta to be large, then our acquisition function is basically the uncertainty. So as I mentioned, GPAX realizes several additional acquisition functions. So UCB, expected improvement, uncertainty-based exploration, so pure uncertainty. There is also Thompson sampling. So we are not going to talk about it because this is a different way to sample Gaussian process. But let's see how it works. So we start with the same installations, and we define the same data generation process. So in this case, so let's wait until it explores. And as before, let's define the Gaussian process priors because they will affect our process very significantly. So let's set our priors on the kernel to be somewhere between 0.1 and 10. So that's actually pretty broad. So in this case, my function is defined with a fairly high noise. So that may be a little bit extreme. So let's set the noise to be actually 0.1. So now it's much better. Let's assume that we believe our measurements. So let's say that this is from 0.1 to 1. Let's assume that our kernel length scale is also have the uniform distribution. Kind of as before, we can visualize them just to make sure that we know what we are talking about. And now we create the cycle for the Bayesian optimization. And you will see that this cycle is very similar to that to the Gaussian processing discovery. And the reason is that that's exactly the reason why the GPAX is defined in this way, in order to make the adaptation for the typical active learning problems as simple as possible. So what we do is we again define a single step of discovery process. So as the input, we have our measurements, X measured and Y measured. We have our parameter space sampling, the X unmeasured. So kind of very logical. We define our random keys. So that's something that algorithm needs. And then the process itself is just 3 lines of code. So the first line of code is defining the Gaussian process model. So it's one-dimensional. We use the Matron kernel. We use kernel priors as defined, and we use noise priors as defined. So very simple. Our second step is the fit of the data, X measured and Y measured, fit by the Gaussian process model. And our third step is the prediction. So as the prediction, we give the average and the sampled, so kind of several, the posterior functions, and we define them on the X unmeasured. So we make the predictions for the unmeasured points. Notice that we have also an argument noiseless true or false. True means that we provide the output without noise. False would be that we also add the noise. So it's more useful to have the noiseless option. So this is where we make the prediction, and this is where we calculate our objective function. So our acquisition function. So to calculate the acquisition function, we take as an input the model, so that has been trained over here. We take as an input the X unmeasured, so we calculate the acquisition function values for the regions where the measurements have not been taken. We take some parameter beta, so this is our hyperparameter that controls the balance between exploration and exploitation, and that's it. So then we return the value of the acquisition function, and we also return the predicted mean function and sampled. So notice that for illustrative purposes, I basically give the opportunity to use the either expected improvement or the uncertainty. So if you want to run it with a different acquisition function, just comment this line and not comment these lines. Now let's see how the Bayesian optimization is going to run. So the cycle here is very simple. So we define the number of steps. So this is our experimental budget. We start with the making a single step. So the step returns to us acquisition function, prediction, and posterior distribution. We choose the point where the acquisition function is maximal. And we basically said that our next point is going to be exactly this x unmeasured. So we choose our next measurement point where there is a maximum of the acquisition function. So then we measure next point. This returns our next value. So notice that here we simply evaluate our ground truth function and that noise. In experiment, this is actually the step where you go to the lab. So the reason why it is a good idea to run through this simulated experiments is to figure out how to tune the models in such a way as to make the convergence faster. Because so when I was young, whatever, 30 years ago as the undergraduate student in Moscow State, our professors used to say that a day in the library can save you a week in the lab. So now we have computers, so we don't have to go to the libraries anymore. But a few hours tuning the algorithm on the past data or using some form of model can save you quite a considerable time going to the lab and making samples. So strong incentive to play with it first. So then what we are going to do is to simply update the measured data. So we update the measured data by adding the point where we do the measurements. We update our y values, and then we plot our results. And obviously our result is ground truth, predicted function, and uncertainty interval. So let's see what happens in this case. So this is our, as before, this is our measurements. This is blue curve is our reconstruction, and the red interval around it is our uncertainty. So given the blue curve and the uncertainty, we calculate the acquisition function. So in this case, the maximum of the acquisition function is here, which basically tells us that the next measurement is going to be done in this location. And then if we continue the process, you can see that the maximum of the acquisition function is actually keeps being here. So why is it the case? It is the case because unlike the discovery process, in this case, we are trying to solve the minimization problem. So we want to find the minimum of the function. And once we run this process, you can see that we managed to find the minimum in essentially our second step. So we hit the true minimum here. And basically, the way we have formulated the problem, the algorithm is now going to start here. It is going to explore the location of this minimum, and it's not going to explore anything else because it has no reasons to do so. It's a minimization problem. It's not a discovery problem. So in this case, it can be kind of interesting to look at how the posteriors look like. So what are this Y sample like? So this is the possible ways the algorithm believes our function can evolve. So it can be like this, it can be like this, it can be like this, but it still already thinks that it found the minimum. Now, the interesting thing, as you can speculate from these observations, the interesting thing is that the Bayesian optimization is absolutely not guaranteed to find the true minimum. So that's very important step, a very important consideration. So if you have the pure uncertainty-based exploration, you are guaranteed to find the true function. The question is how long it is going to take. It may take longer. The reason why we are going through this examples of training how to tune the hyperparameters is because we want to learn how to find it in smallest amount of steps possible, not to waste our experimental time. But we have the theoretical assurance that we will always find the true function. For the Bayesian optimization, there is no assurance. So if we choose a sufficiently greedy policy, we can easily get trapped in the false maximum. So in this case, we got trapped here, but if I tweak the parameters values a little bit, I can easily find the situation when I get trapped in this minimum. And once you are trapped, then the exploration will stop. So how can I change this dynamic? So one way I can change this dynamic is simply to run the active experiment by I can simply run active experiment by increasing the exploratory component. So let me get to our beta, and I can make it 50. So 50 is a lot. Let's see how it's going to work in this case. So in this case, I basically say that, you know what, I want to invest more cycles into the exploration of the system, which basically means that I pay much more attention to what happens in the regions with the high uncertainty compared to the regions where the uncertainty is small, but the function is minimal. So let's see how it's going to behave in this case. And again, if you have questions about the process of what we are going on, please don't hesitate to put them in chat, because kind of the best way for get the answers is to ask questions. Okay, so it looks like that in this case, there is actually not much difference. So even though we decided that we are going to be more curious, the behavior of our discovery process didn't change much. So let's see why it might be happening. So let's get to the end. And here we go. No, actually it did change. Look, so in the previous set of experiment, when our sigma was, our beta was small, we got stuck here. And now you can see that we are starting to run the additional experiments here. So we decided that we are close enough to the minimum. And now our acquisition function is has maximum here and here. So in these locations. So in fact, we spent some experimental budget in order to perform measurements here and here. So we actually perform measurement not at the minimum, but at the locations close to the minimum. So the question you may ask is, what is going on? Why is that our function uncertainty is so high? Well, let's look at how we have chosen our priors, and notice that our noise prior is sufficiently broad. So let's assume that we make it smaller and use the half normal distribution. And this is fine, and our data generation process, okay, we can make a noise smaller here. So let's see what happens in this case. Redefine our priors, run the whole experiment one more time. Let's see what happens. Let's see what happens next. Okay, excellent. So we start with these measurement locations. We calculate our, sorry for that. We do the GP reconstruction, so the uncertainty is large here and here. So our next measurement point is here. We do the measurement here, so we try to reconstruct our function again. So this is again our acquisition function. So the next measurement would be again kind of close to 0. So the next location is here. So after that, notice that even though we want to minimize the function, we choose to do the measurement when the uncertainty is very large, because we want the measurements to be to favor the exploration. What we are going to get is obviously we are going to reconstruct the function here. So this is our next location. And finally, as the next step, we want to do the better reconstruction in this location. So that's kind of as far as we get in 5 steps. And now let's, as the last, as you can see, in this case, when our exploration, our process is exploration dominated, so we want to explore more so than find the minimum, we actually start to reconstruct our function sufficiently well. So it almost looks like a normal GP-based reconstruction. Now let's run this experiment one more time and call it a day after that, when we actually go for a very greedy process. And to do the very greedy process, let's choose the beta to be 0.5, so a very small value. So let's run the Bayesian optimization in this case. So same parameters of the noise prior, noise and the data generation process on the kernel priors. But the thing that is different now is that now we choose to be greedy. We really want to go for local optimization as much as possible, and we really don't want to spend any time exploring things. So look what's going on here. Again, these are our measurement points. This is our reconstructed curve. This is the uncertainties. Look at our acquisition function. So now the acquisition function has the maximum here. And the reason why it has maximum here is because we believe that the reconstruction has a minimum here. And notice that this minimum is close to the true minimum, but this minimum is also close to the one of the metastable minima. So let's see if the process will converge to this one or this one. So this is the right one. This is a trap. So where are we going to go? So first measurement is done here. Second measurement is going to be done here. So it looks like that in this particular case, we actually starting to discover the true minimum. And yes, it worked. So our next step is here. Our third step hit the true minimum. And if we continue the process, we are going to keep doing the measurements over here. So in this case, our policy was fairly greedy, but still the beta equal to 0.1 allowed us to find the true minimum value. Well, let's try to do it one more time, just out of curiosity, but let's make beta really small, sort of almost 0. So let's see what happens in this case. So let's see the process one more time. So again, since we fixed the keys, in this case, our measurements are kind of reproducible. We always start with the same points. So let's see what goes on. So our first measurement is done here again. So let's see what happens with the second measurement. So our second measurement is done here. So let's see whether we are going to discover the true minimum or false minimum. So it looks like the next measurement is 0.7, so it is here. Let's see what happens with the third. Okay, so it looks like that in this case, we still discovered the true minimum. But okay, fine. So in this case, we got lucky, but again, if the true minimum was this one, we would not discover it. So in this case, it's kind of close. So this being the said, sort of let's stop the collab here. So again, I have suggested several experiments that you can play with. So kind of, first of all, make sure that you keep track of the codes, whether you want to maximize or minimize function. So that depends whether you choose true or false argument. And also you need to choose either argmin or argmax for the step. So whether you want to maximize the acquisition function or not. And then there is a series of the experiments you can try in order to, with some explanation, in order to get a better feeling of how the Bayesian optimization works, how does the balance between exploration and exploitation works, and basically get the idea of how the algorithm behaves and what is the probability to get trapped in the wrong minima. So again, when we work with the synthetic data sets, then we know whether we are trapped or not. If we work with the real world situations, we of course don't. So in those cases, we would not be able to find out whether we are trapped or not. So this being said, let's call it a day. And if you have questions, now is a good time. If not, then till next time. Okay, so thank you for listening. And kind of just as the reminder, in order to get the maximum benefit from the course, play with the code. That's truly the only way to learn. So the things that we discuss is help you guide through it and the focuses on the important concepts. But the only true learning in these cases is the hands-on learning. So absolutely. Yeah, so the notebooks are all on the GitHub associated with the course. And once moving in the lab and higher dimension, that's when the life becomes actually more fun. So that would be a great thing to explore.